Hello, it is me, Ugo. So we are going to be doing the matrix search problem, or on LeetCode it's called search a 2D matrix. So let's just look at it right here. They have a slightly different implementation or requirement where we have to return an integer. It's still gonna be false and true, so it's kind of the same thing, just uses an integer instead. It's fine. Um, so basically, all that's gonna happen is we're gonna be given a 2D matrix of integers. So we're gonna have a 2D list and it's going to be sorted. And sorted 2D matrix means that the greatest element of the previous row is smaller than the smallest element of the next row, and the rows are individually sorted in ascending order. So as you can see, we have 1, 3, 5, 7. 7 is the greatest here. It's going to be at the right because we're going in ascending order. And then we're going to check, okay, 7, is it less than 10? Yes, so we we have the previous row, all elements in it are less than the smallest one here. We keep going forward, 20, 23, same thing happens there. So the problem wants us to do, or it gives us a 2D matrix, and it also gives us a target number, and all we're supposed to do is look for the target number. If the target number is in the matrix, we return 1 or true, depending on where you're doing it. And if it's not there, then we return 0 or false. So that's pretty much the problem. Um, the size of the matrix can be 100 by 100, and the target is between negative 104 to 104. So it's not going to be a big number, and the matrix can be kind of big. I don't know. I don't know if this is considered big in programming though. I mean, I feel like 100 by 100 is a lot, but might be small for a computer. So, yeah. So like in this example, we're looking for 11. 11's right here. We're looking for 18 in this one. 18 is not here. As you can see, it's 16 and 20. There's no 18 between them, so it's not there. I don't know if it says it here. It just says use an efficient algorithm, but the actual LeetCode problem says you must write a solution that is O of log m n time, where m and n are the row and column sizes, or the number of rows and columns for each row. So using the fact that it's sorted and the fact that we need a logarithmic time complexity, we can assume that we're probably going to need to use binary search. Just how do you use binary search on a 2D matrix? So, um, that normally would be tricky to figure out, but thankfully I took a class for multimedia, and in that class, during one of the homework assignments, I found out this neat little trick where you can essentially um, flatten a 2D matrix if you have the number of columns, and the number of columns is consistent throughout the matrix. So for an image, you'd have a 2D, like a square, and there's going to be pixels in each row, and each column is going to have, or there's going to be a certain number of columns for each row. So we could go through it without having to use, double for loop. I don't know if that was more efficient or not, but I thought it was a pretty cool trick. And that stuck in my mind when I first looked at this problem. So I just tried doing the same thing and it worked. So basically, what we're going to take advantage of, let me see if I can open up OneNote. Let's see. Okay. So really quickly, I mean, it's not going to be a crazy drawing. What was I going to draw again? I was going to draw the, oh, right. So we have, let's say we have 3 rows, right? Oops, that one looks more like a sphere, but it's fine. So let's say we have 3 rows and each one has 4 columns. So if we wanted to flatten it, or well, at least in this case, okay, so if we have the 2D list, each one of these rows is an element within a larger list. So it's a list of lists. And each one will go from 0, 1, 2, oh, sorry, I'm doing it with my mouse. 0 to 3 in indices, and it'll repeat that. However, if we wanted to flatten it so we could use binary search on it, we could just try to treat it like this. So we do 3, but instead of restarting to 0, we just continue at 4. And then 5, 6, 7, 8, 9, 10, and 11. So the binary search would be the equivalent of just having one giant flat list where we have like all of these things in there, and then we would get the middle point. In that case, it would be right here, somewhere in here, one of these two. So what we can do is we can actually take the size of the row, so the list inside, and that will give us the number of columns. And then we could use modulo of the number of columns to get whichever column we're currently looking at. And this works because if we looked earlier, it always has the same number right here, and it goes from 0 to 4. And then it goes back to 0 here, 1, 2, and 3. So if we did modulo, I don't know, 5 modulo 4, we would get 1. If we did 6 modulo 4, we get 2. So we can have we can have a 2D list where we just treat each index, or we treat the size like n times m rather than each one individually by row. And this allows us to find the indices in the middle. So now we just need to figure out how to find the column in our row that we're currently looking at. And this is how we find the column. However, how do we find out the row? Well, when we look at these values, we're going 0 to 3, and after completing 4 columns or going through 4 columns, we're going to go back to the beginning of the next one. So it's like this is index 0, 1, and 2. And if you notice, 8 divided by 4 is equal to 2. 4 divided by 4 is equal to 1. 0 divided by 4 is equal to 0. And the reason that this works is because we're doing integer division. So if we're looking at a column, like let's say 2 integer division of 4, that'll give us 0. So all of these elements, if they're smaller than 4, then that means we're going to row 0. If they're bigger than 4, or bigger or equal to 4, but smaller than 8, then they're going to go to row 1. So what we can do is we can simply get, or flatten, not flatten, but like basically use n times m for the size of the matrix. So we can start with the left at 0, like normal. Then we can start the right at n times m. So then we have the flattened list, or we see the indices as flat. But then when we actually look for the mid, what we're going to do is we're going to divide it by 4 for the row, which will get us the row number that we're currently on. So it'll get us to the list that we want. So it's going to get us 0, 1, or 2. So if we had, I don't know, let's say 9, right? Or at the start, I guess it would be, let's see, it would be 12. So, or well, we want to do subtract by 1. So then we have the 0 index. So it would be, what would that be? The midpoint would be, let's see, it would be 11 divided by 2. That would give us 5, integer division. So we're going to start at Wait. Oh, 5 is the midpoint. So the 5 index, in the index that we currently have labeled as 5 right here, so this one is the mid. And then we're going to do integer division by 4, which is the number of columns. And that's going to get us the row number that we're currently looking at for the midpoint. 5 divided by 4 is going to get us a 1 with integer division. And is that true? That is the middle row. And then now we're going to look at the column. So the column is just going to be the middle number that we currently have modulo 4. So then we figure out whether it's 0, 1, or 2, or 3 in the columns. So in this case, we're going to have 5 modulo 4, which will get us 1, as seen earlier. Oops. And is that true? Well, we go 0, 1, and here's the 5. So it's at row 1, column 1, and that is true. And then we just do binary search like normal. So that's essentially the problem. Sorry if I blinded you. Yeah. If we look at the actual code, it's literally just that. We get the number of columns. The number of columns is going to be consistent throughout the matrix. So we could just get the first row, the size of the first row, and that's going to give us the number of columns. And the right will be the length of the matrix. So this will be the number of rows and the number of columns subtracted by 1. So then we have it 0 indexed. And then we're going to have left start at 0, obviously. We're going to do left is less than or equal to right. So we're going to keep going until that condition fails. If that condition fails, then it's not going to be in it. That's just normal binary search. We're going to do this one. This is the mid formula that prevents us from getting integer overflow issues. So you just subtract by right from left and then divide that by 2 and then add left to it. And then right here, this is just for readability, I think, or in my opinion. I don't know. I don't know if it's better or not. Maybe I shouldn't have done it because you had to store them as integers and reassign them every time. But I wanted to make it more readable. So the row is going to be the number, the mid that we're currently at. So the middle index that we're currently looking at with integer division of the number of columns that we have. So like I said in the previous case, we had 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The number of columns would cause us to figure out which row we're currently looking at. And then the column, we figure out which one we're looking at by doing modulo of number of columns. So look at whether we're at the 0, 1, 2, or 3 indexed for the column. And we just use that, and we just do binary search like normal from there. So we look, is the current row and column equal to the target? If that's the case, then it is in it. Otherwise, if it's to the left, if the value that we're currently on is less than the target, we're just going to move left upward to the past the mid. Otherwise, we're going to move right backwards toward behind the mid. And if this condition ever fails, that means we didn't find the target inside of it. So we just return false in that case. And yeah, that's the solution that I got for the binary search, or the search matrix problem. Search a 2D matrix. It uses of log m n time, where m is the number of rows and n is the number of columns. And we don't use any additional space because we don't have to. We just flatten the list. Well, we don't really flatten it, actually. We just use mathematical. I don't know if it's mathematical, but we just take advantage of the fact that since there are only going to be so many columns, and each time we go past that number of columns, we go back to another row, we can just use that to find the row and column that we're currently at based on the number or the size of the first row, which would give us the number of columns in each row. So it's like, technically it's not flattening it because we don't do anything to the list. We're just treating it as a flattened list with this property right here. It's pretty cool. I love it. I've used it multiple times now. amazing property. I just, if you had to learn anything from the video, learn this. It's so helpful. It's so cool too. But yeah.